Welcome to Curiosity, the podcast where science meets wonder. Join us as we explore the fascinating, the innovative, and the unexpected, from the secrets of the cosmos to the marvels of everyday life. Each episode takes you on a journey to uncover the knowledge and stories that fuel our endless quest for understanding. Let your curiosity guide you.
I want you to do something for me right now. I want you to stop what you're doing just for a second and look at your hand.
Oh boy.
No, seriously, flex your fingers, turn it over, or if you're driving, maybe just feel the grip of the steering wheel. Knock on the desk in front of you.
Please keep your eyes on the road if you are driving. Safety first.
Absolutely. Eyes on the road, definitely. But the point is, engage with the physical world for a moment.
Okay.
Classically, when we do that, when we, touch a rock or see a tree or feel the wind, we assume we're interacting with stuff.
Right. Matter. Energy.
Exactly. It feels solid. It feels like the bedrock of existence. It's undeniably there.
It's the intuitive view. It's what our senses, scream at us from the moment we're born.
Right. But what if I told you that our senses are lying? What if I told you that the bedrock of reality isn't matter at all?
Oh.
What if that rock, that hand, that steering wheel are actually illusions?
That is a very heavy way to start. You're going straight for the existential crisis today.
I'm going big. Because today, we are analyzing a stack of research that presents, arguably, the most radical shift in physics since Einstein.
It's a big one.
We're looking at evidence suggesting the universe is not made of particles or fluids or solid objects. It's made of code.
Information.
Information. It's made of information.
That is what is known in the scientific community as the digital physics hypothesis.
Right. And I want to be clear right off the bat. This isn't just some, stoner philosophy or a sci-fi writer's fever dream. We aren't just talking about the matrix here, though we will get to that. We are talking about hard physics. We're talking about quantum mechanics, thermodynamics, and the behavior of black holes.
Yep.
The argument from these sources is that the universe is fundamentally a vast computer.
It is one of the most profound and, frankly, controversial ideas in modern science. But you are right, it isn't fringe in the sense of being ignored.
Not at all.
It solves specific mathematical problems that standard physics just.
Yeah.
It just can't touch.
So our mission today is to unpack this whole idea. We're going on a journey into the data to understand this phrase, it from bit.
It from bit, a classic.
We're going to find out why a black hole might actually be a kind of hard drive, why space itself might be a hologram, and why your consciousness, your very thoughts, might just be data processing.
It is a complete inversion of how we usually view the world, a total flip.
Let's start exactly there, the great inversion. Because to understand why this is so radical, we have to understand what we're pivoting away from. What's the old way? The standard model we all grew up with.
Well, the old way is essentially the classical scientific worldview. It's the Newtonian framework, updated with some 20th century particles.
Right.
In this view, reality is made of two main constituents, matter and energy.
Electrons, quarks, photons. The Lego bricks of the universe.
Exactly. Couldn't have said it better. Matter is the stuff that occupies space and has mass. Energy is the capacity to do work or cause change. These things interact according to fixed mathematical laws, gravity, electromagnetism, and so on.
And it's all very concrete.
Very. But the crucial philosophical stance of the classical view is realism.
Meaning it's real, whether I'm here or not. The tree in the forest still falls.
Precisely. If you leave a rock in the forest and walk away, the rock is still there. It has mass, it has shape, it has a definite position. It doesn't care if you're looking at it. It exists independently of any observer.
Right. And in this old way, where does information fit in? Because we talk about information all the time now. It's the information age.
In the classical view, information is secondary. It's derivative.
Derivative how? What does that mean?
Think of a map of London. The map contains information about London. It tells you where the streets are, where the river is, but the map is not London.
Of course not.
London is the territory. The map is just a description we created to help us navigate. In classical physics, information is just a pattern we extract from matter. It's our notes on the universe, not the universe itself.
Okay, that makes perfect sense. Matter comes first. Information is just the label we put on the jar.
Correct. Now, digital physics flips that script entirely. This is the inversion.
So in the digital physics view, the label is the jar.
Even more than that, the hypothesis argues that information is fundamental. It is the bottom layer of reality.
And matter. Energy.
Matter and energy. Those are just emergent phenomena. They are manifestations arising from the underlying information processing.
That is genuinely hard to wrap your head around. It feels completely backward. How can information exist without something to hold it?
The source material uses a great analogy that helps visualize this. Think about your computer screen right now, or your phone screen. If you look at a picture of a dog on that screen, what do you see?
I see a dog. I see brown fur, a wet nose, a shape. It looks soft. It looks like a dog.
Right. It looks like a solid object. It has boundaries. It has color. But if you get out a magnifying glass and look really, really close, what is it really?
It's pixels. Just little dots of light, red, green, and blue dots.
And deeper than the pixels, what's making them light up?
It's electric current. Transistors switching on and off inside the processor. Voltage states.
Zeros and ones.
Yeah, binary code.
Exactly. The dog is an emergent property. The dog emerges from the processing of information. The information, the bits, are the fundamental reality of that computer. The image is just the user interface.
Okay, I see where you're going.
Digital physics asks a simple but terrifying question. What if the universe is the screen?
Meaning atoms are the pixels.
Yes. What if atoms, electrons, and quarks are just the pixels and the real reality is the code running underneath them?
That is a wild thought.
Yeah.
It implies that everything I can touch, this table, this microphone, is basically just a GUI, a graphical user interface for a cosmic operating system.
In a manner of speaking, yes. The solidity you felt when you knocked on the desk.
Yeah.
That's just the rules of the code preventing your avatar from clipping through the environment. It's a collision detection algorithm.
Okay, wow. Before we go further down this rabbit hole of whether I'm just a localized error in the code.
A feature, not a bug.
Right, we need to establish the pedigree here. Because if you just say the universe is a computer, it sounds like something you realize at 3 a.m. after too much pizza. Who actually came up with this? Is this just one guy in a basement, or are these serious scientists?
Oh, these are very serious scientists. This isn't a fringe internet theory born on Reddit. This traces back to some of the absolute giants of 20th century physics.
Let's talk about the pioneers then. The outline highlights John Wheeler. Now, Wheeler isn't just a nobody, right?
John Wheeler is a titan, an absolute titan. He was a colleague of Einstein and Niels Bohr. He's the man who popularized the term black hole.
No way, that was him.
That was him. He was at the center of theoretical physics for decades. In the late 1980s, he proposed a concept that really sums up this entire episode. He coined the phrase, it from bit.
It from bit. It's catchy, I'll give him that, but unpack it. It sounds a little like a marketing slogan.
It does, doesn't it? But it's a profound ontological claim. And Wheeler argued that every physical it, every particle, every field of force, even the fabric of spacetime itself, ultimately derives its function, its meaning, its very existence from binary choices.
Binary choices.
From bits, yes-no answers.
So he's saying you can't have the particle without the information that defines it.
He's going even further than that. He's saying the information is the primitive concept. The particle is secondary. He speculated that the universe, at its core, isn't made of some kind of fluid or substance, but of yes-no answers. Is there a particle here, yes or no? Does it spin up or down? Up or down?
He's reducing reality to a game of 20 questions.
That is exactly the metaphor he used. He said nature is like a game of 20 questions where we ask yes-no questions, and the answers build up the reality we perceive. He believed that at the bottom of everything, when you strip away the electrons and the quarks, you don't find a thing. You find a question and an answer.
That sounds suspiciously like computer code. Binary, zeros and ones.
Which leads us to Konrad Zuse. Now, Zuse isn't a physicist by trade. He was a German civil engineer and a computer pioneer.
Okay.
In 1967, he wrote a book called Calculating Space. He was one of the first to look at the laws of physics and say, wait a minute, this doesn't look like analog mechanics. This looks like a computation.
He proposed the computable universe.
Yes. He suggested that the entire universe is being computed on a vast deterministic machine. This was decades before the matrix or modern simulation theory. He was looking at the discrete nature of nature and seeing algorithms. He thought, if nature's doing math, maybe nature is the computer doing the math.
Wow, in 67, that's incredibly prescient.
It really was.
And then we have Edward Fredkin in the 90s. He took this and ran with it into something called digital philosophy.
Fredkin is fascinating. He proposed that the universe is a cellular automaton.
A cellular what now? That sounds biological.
It does, but it's purely mathematical. Imagine a giant grid, like an infinite checkerboard. Each square on the board, each cell can be in one of two states, on or off, black or white.
Okay, I'm picturing an infinite checkerboard.
Now imagine there is a clock. Tick, tick. At every tick of the clock, every square checks its neighbors. It follows a very simple rule, something like, if 2 or more of my neighbors are black, I turn black, otherwise I turn white.
So just simple local rules.
Incredibly simple rules. But what Fredkin and others like John Conway with his Game of Life showed is that if you start with a simple grid and simple rules, incredible complexity emerges.
Like what kind of complexity?
You get patterns that look like moving objects. They call them gliders. You get things that reproduce. You get things that look like chaos. You can even build a working computer inside the grid just using these simple on-off cells.
So Fredkin argued the universe is just that, a giant 3D checkerboard.
Yes. He argued that space is discrete, it's made of tiny chunks, and time is discrete, it moves in ticks. And the laws of physics are just the update rules for the grid. He believed that if you zoomed in far enough, past the atoms, past the quarks, you would eventually see the grid, the pixels of reality.
So we are just the complex patterns in a cosmic game of life.
Yay.
That's humbling. It means the complexity of love, art, and war is just simple rules repeated a trillion times.
It is. And then, bringing it closer to the present, you have Seth Lloyd at MIT. He tweaks this slightly. He argues that the universe isn't just a classical computer like Zeus thought, it's a quantum computer.
Because, well, quantum mechanics exists. It's not just zeros and ones.
Right. A classical computer uses bits, 0 or 1. A quantum computer uses qubits, which can be 0, 1, or both at the same time. This is superposition.
Right.
Loy argues that the universe processes information using the laws of quantum mechanics, superposition, entanglement to compute its own history. The universe is a quantum computation.
Okay, so we have these brilliant minds wheelers, Zeus, Fredkin, Lloyd, all pointing in the same direction, saying, hey, this looks like a computer. But why? What is the evidence? Because usually when physicists agree on something this weird, it's not because they want to, it's because the math forced them to.
And that is exactly what happened. The evidence primarily comes from the weirdest corner of science, quantum mechanics.
I feel like every time reality gets weird, quantum mechanics is the culprit. It's the usual suspect.
It usually is. To understand why physicists started thinking about information as fundamental, we have to look at the measurement problem.
Okay, break this down for us, but keep it simple. How does measurement relate to code?
Well, think about a video game. Let's say you're playing a vast open-world game, something huge. You're standing in a room. Does the computer render the room next door?
No, it would crash the system. It only renders what I'm looking at. It's called frustum culling or something, right? It saves processing power.
Exactly.
Yeah.
The room next door exists as data on the hard drive, as potential, but it doesn't exist as a rendered image until you walk through the door and measure it with your virtual camera.
Okay, I get that.
Quantum mechanics suggests the universe behaves almost exactly like that. In classical physics, an electron has a definite position and speed at all times. Even if we aren't looking, the electron is somewhere.
Right, the old realism we talked about.
But in quantum mechanics, that view just breaks down. Before you measure a quantum system, it doesn't have definite properties. It exists in a superposition of states. It is described by a wave function, which is basically a list of probabilities.
So not a thing, but a list of possibilities.
A list of information about what could happen. The electron could be here or there or over there all at once.
So it's just a cloud of possibilities.
Until you measure it. The act of measurement collapses that wave function into a definite state. Suddenly, the electron is here.
So the measurement creates the reality.
That is the Copenhagen interpretation, and it's the one digital physics leans on heavily. It suggests that properties like position or spin are not intrinsic to the matter. They are created when we access the information, when we look.
That sounds suspiciously like the video game engine rendering the room only when I open the door.
It's the classic analogy. It suggests that the wave function, which is pure information, a list of probabilities, is the real thing, and the physical particle is just the runtime output. It implies the universe is optimizing resources, only defining reality when an interaction, a measurement, requires it.
That is deeply unsettling. It implies efficiency, like the universe is saving RAM. But there's more. We have to talk about entanglement.
Ah, entanglement. Einstein's spooky action at a distance. This is the other big tiller here.
So what is it again?
You can have two particles that are entangled. That means they share a single wave function. They are mathematically linked, described by the same piece of information, no matter how far apart they are.
Yeah.
If you measure one and find it spinning up, The other one instantly, and I mean instantly, snaps into the down state.
No matter how far apart they are.
No matter how far. One could be in this room, the other could be in the Andromeda galaxy, 2.5 million light years away. The connection is instantaneous.
Which Einstein hated, right? He called it spooky action at a distance because nothing is supposed to travel faster than light. If I poke particle A, how does particle B know to react instantly? The signal can't get there fast enough.
Exactly. If you view this as two separate physical objects in 3D space sending a signal to each other, it's impossible. It breaks the fundamental speed limit of the universe. But if you view it as an informational structure, it makes perfect sense.
How so?
Think of a video game again. Imagine you have two characters on the screen. They are miles apart in the game world. But in the computer's memory, their data might be stored right next to each other.
Okay.
Or better yet, think of a single variable in a program. Let's call it game state. This variable is referenced in two different places on the screen. If I change the game state variable to night in the code, the sky in both places on the screen instantly changes to night.
Because there was no signal traveling across the screen from one point to the other. The change happened at the source code level, and both points were just reading from that same piece of code.
Precisely. Digital physics argues that entanglement shows that the distance between particles is, in some sense, an illusion. In the underlying informational structure, those particles are adjacent. They are just the same bit of information being displayed in two places.
So entanglement suggests that that space itself might not be fundamental.
It suggests that space-time might be emergent. The geometry of the universe, the distance between things, might arise from these deeper patterns of entanglement. We are seeing a 3D world, but the underlying connections are purely informational, and they can ignore space entirely.
Okay, so quantum mechanics is basically screaming, it's all information at us. But then we get to the really heavy stuff, the biggest objects in the universe, black holes.
Yes. This is where thermodynamics meets gravity, and it's where digital physics gets its strongest, most mathematically rigorous argument.
I love that we're just casually dropping black hole thermodynamics into the conversation like it's light brunch talk.
It's fascinating stuff, I promise. We have to start with entropy.
Entropy is disorder, right? The tendency for things to get messy. My office is a testament to high entropy.
That's the classical definition, yes. But in the 1940s, a brilliant mathematician named Claude Shannon, the father of information theory, redefined entropy. He defined it essentially as a measure of hidden information.
Hidden information. How does that relate to messiness?
Think of a perfectly clean room versus a messy room. A clean room is low entropy. It's easy to describe. The socks are in the drawer, the books are on the shelf. Very little information needed to describe its state.
Right. It's orderly.
Now think of that messy room. Socks are everywhere. Dust is everywhere. To fully describe the exact position and orientation of every speck of dust and every single sock, you need a massive amount of data.
A ton of information.
Exactly. So high entropy means high information content. Lots of detail is hidden in the mess.
Okay, I follow. Messy equals lots of data. So how does this connect to black holes?
So, in the 1970s, physicists like Jacob Bekenstein and Stephen Hawking started looking at black holes. And they asked, what happens to the information of a star or a planet or my diary when it falls into a black hole?
If I throw my diary into a black hole, is the information in that diary lost forever?
Physics says information cannot be destroyed. It's a fundamental law.
Yeah.
The universe has to keep a record. So they tried to calculate how much information a black hole can hold. Now, intuitively, how much stuff you can fit in a box depends on the volume of the box, right?
A bigger box holds more stuff. If I double the radius of the box, I can fit 8 times the amount of stuff. It's a cubic relationship.
Exactly. That's our 3D intuition. But when Bekenstein and Hawking did the math for black holes, they found something that shocked everyone. The entropy, the information capacity of a black hole is not proportional to its volume.
It's not.
It is proportional to its surface area.
Oh, wait. So it's proportional to the skin of the black hole, the event horizon?
Yes. The two-dimensional boundary. Imagine a library where the number of books you can fit inside doesn't depend on how much room is inside, but on how much wall space you have to paint the titles on.
That doesn't make any sense for a normal physical object.
Correct. Which is why this was such a revolutionary insight. It suggests that the 3D interior of the black hole, everything inside, is actually fully described by the data encoded on its 2D surface.
So the inside is just a projection of the outside.
In a very real mathematical sense, yes. The 3D reality is redundant. All the necessary information is on the 2D boundary.
And this led directly to the holographic principle.
Right. It did. This is the concept proposed by Gerard Hooft and Leonard Susskind, and then powerfully demonstrated by Juan Maldacena. They took that black hole insight and applied it to the whole universe.
The whole universe.
The idea is that the entire 3D universe we experience with depth, volume, stars, galaxies, you and me, might be a hologram.
Okay, define hologram here. We aren't talking about Tupac at Coachella.
Right, not that kind of hologram. Think of the hologram on your credit card. It's a flat 2D sticker. But when the light hits it just right, you see a 3D image floating there. You can look around it. It has depth. But if you touch it, it's flat. The 3D image is a projection of 2D data.
So the holographic principle says our reality looks 3D, feels 3D, but is mathematically equivalent to a flat 2D system.
That is the implication. It suggests that the 3D world, the volume is not fundamental. It's derived. The real data exists on a distant 2D boundary, essentially the edge of the universe.
That completely challenges the reality of space itself. If I walk forward, I'm not really moving deeper into space. I'm just navigating a data projection.
Precisely. It connects back to the digital physics hypothesis perfectly. If the universe is a hologram, then matter is definitely an illusion in the way we think of it. It's all just information processing on a 2D surface, giving the appearance of a 3D world.
I need a second to process that. I'm looking at my hand again and trying to imagine it as a 2D smear of data projected from the edge of the universe. It's not easy.
It's a difficult visualization. But mathematically, the ASCFT correspondence, which Maldacena discovered, shows that this is theoretically possible. He proved that a complex 3D gravitational world can be mathematically equivalent to a simpler 2D quantum world without gravity. They're the same thing, just translated into different languages.
Okay, so let's assume for a second this is true. We are in a computational universe, a digital reality.
Yeah.
That brings us to another huge mystery that has always bothered me. Time.
Ah, yes. The arrow of time.
Physics has always struggled with this, right? Most of the fundamental formulas work forwards and backwards. If you play a video of planets orbiting backwards, it still looks like valid physics. But in real life, eggs break, they don't unbreak. We get older, not younger.
Correct. The laws seem symmetric, but reality isn't. We call that the second law of thermodynamics. Entropy always increases, but digital physics offers a new way to look at it.
The algorithm of reality.
Right. If the laws of physics are algorithms, then the evolution of the universe is simply the execution of the code.
So the universe is computing itself into existence.
Step by step, moment by moment.
And that solves the time problem. How?
It offers a solution. Why does time move forward? Because computation is sequential. You have to calculate step 1 before you can calculate step 2. The arrow of time is the direction of the computation.
That makes intuitive sense. You can't run a program backward and get the input from the output easily. If I give you the number 4, you don't know if I calculated 2 plus 2 or 3 plus 1. Information is processed in a direction.
Exactly. And regarding entropy, why does it always increase? Because as the universe computes, it explores more and more computational states. The information structure changes, evolves, and generally becomes more complex. We perceive that increasing complexity as entropy.
So time isn't just a dimension we travel through. It's the processing speed of the universe.
That is a very digital way to put it, yes. The tick rate of the cosmos.
Okay, here is the question everyone is waiting for.
Yeah.
We've established the universe acts like a computer. It processes info. It has pixels, or quanta. It renders on demand. It has a refresh rate, which is time. So, is someone else using the keyboard?
You are talking about the simulation hypothesis.
I am. If it's a computer, is it our computer, or are we inside someone else's simulation?
This is where we have to be really careful. Digital physics and the simulation hypothesis are related, but they are not the same thing.
Okay, distinguish them for me. Because to the layman, they sound almost identical.
Digital physics is an ontological claim. It says the stuff of the universe is information. It doesn't say who or what built it. It could just be that information is the natural, fundamental state of existence. It doesn't require an external creator.
Okay. A self-organizing system of information.
Exactly. The simulation hypothesis, popularized by philosophers like Nick Bostrom, takes that extra step. It posits that we are running on a computer built by a more advanced civilization, that there's a simulator.
Bostrom has that famous statistical argument, right? The trilemma.
Yes. It's a clever piece of reasoning. He argues that one of 3 things must be true. 1, civilizations almost always go extinct before they reach a post-human stage where they have massive computing power.
So we blow ourselves up before we invent the Matrix. Grim. 2, they reach that stage, but for some reason they have no interest in running ancestor simulations. Maybe they find it unethical, or maybe it's just boring to them.
Or 3.
3. They do run simulations, and since they have massive computational power, they don't just run 1 or 2, they run millions of them.
Okay.
Therefore, statistically, there are millions upon millions of simulated minds for every one real biological mind. So if you find yourself being a conscious mind, the odds are billions to 1 that you are in a simulation.
It's a dizzying thought. It's hard to argue with the math, assuming the premises are true. But is there any physics to back up the sim part specifically? Or is it just a philosophical numbers game?
There are some physicists who have actually proposed looking for artifacts.
Like glitches in the Matrix. Are we looking for cats walking by twice?
Sort of, but more like limitations in the resolution. James Bean at Brookhaven National Lab suggested that if we are in a simulation, the simulator has finite power. It can't calculate everything to infinite decimal places, so we should see pixelation.
We might find limits on the precision of physical laws. Or grid artifacts in the way high-energy particles move through the cosmos.
Like with cosmic rays.
Exactly. Cosmic rays are extremely high-energy particles flying through space. If space is a discrete grid, like a computer memory array rather than a continuous, smooth fluid, these particles might prefer to travel along the grid lines rather than diagonally. We call this rotational symmetry breaking.
Have we found any of these artifacts? Any signs of the grid?
Not definitively. We have looked at the cosmic microwave background and the distribution of cosmic rays, and so far, space looks pretty smooth. Annoyingly smooth.
So no grid lines yet?
No. And there are some pretty strong counter-arguments to the simulation theory.
Like what?
Well, the most obvious one is the infinite regress problem. If we are in a simulation, what is the simulator's universe made of?
Right, is it a simulation too? And the one above that, it's turtles all the way down.
Eventually, you have to hit a base reality. And if that base reality is physical, why can't ours be? Why add the extra layer? It violates Occam's razor.
Also, isn't it a bit too convenient? The aliens are just too good at coding for us to catch them. It sounds a bit like saying God works in mysterious ways.
Exactly. That is the falsifiability problem. If the simulator is good enough, they can just patch the glitches before we find them. Or maybe they programmed us not to notice them. At that point, it stops being science and starts being something closer to faith.
Fair enough. Let's pivot to something that feels very real to me, even if I am a simulation. My own mind. Consciousness.
The ghost in the machine.
If the universe is bits and bytes, what is a thought? What is a feeling? How do we get from 0 to 1 to I love my kids?
Now, this is one of the most speculative, but also one of the most fascinating applications of the theory. If reality is information, then consciousness must be a form of information processing.
Which implies that maybe AI really can be conscious one day if we get the processing right.
It does, and it points to theories like Giulio Tononi's integrated information theory, or IIT.
What's the core of that theory?
Tononi argues that consciousness isn't about what you are made of, neurons versus silicon chips. It's about the structure of the information flow. He defines consciousness as integrated information.
Integrated how?
Think of a hard drive. It contains terabytes of data, but the data for one file doesn't know about the data for another file. It's all segregated. Its measure of integration, which he calls phi, is very low.
Okay, a bunch of separate files.
But the human brain is different. When you see an orange, you don't just process color.orange and shape.round and smell.citrus separately. You have a single unified experience of an orange. All that information is woven together inextricably. Tononi argues that this integration is consciousness. The more integrated the information, the more conscious the system.
And digital physics supports this.
It fits very nicely. If the fundamental stuff of the universe is information, then consciousness isn't some magical spirit injected into matter from outside. It's just what happens when information processing gets complex and knotted up with itself.
This sounds a bit like panpsychism, the idea that everything is a little bit conscious.
It leans that way, yes. Panpsychism is the idea that consciousness, or at least the capacity for it, proto-consciousness, is inherent in all matter. In this context, the capacity for consciousness is inherent in all information processing.
So a rock has very, very low integrated information, so it has almost zero consciousness. A human has incredibly high integration, so high consciousness.
Correct. But there is a trap here, a big philosophical pothole that critics always point out.
Oh, well, what is it?
The difference between syntax and semantics, or what some call the challenge of meaning.
Break that down for me.
Think of a computer program that translates Chinese. It can take Chinese symbols in and put correct English symbols out just by following a set of rules. That is syntax, rule following. But does the computer understand Chinese? Does it know what the symbols mean?
No, it's just matching patterns.
Yeah.
It doesn't have the experience of the meaning.
That is semantics. Meaning. Humans experience semantics. We experience meaning. A computer can process the hex code for the color red, but it doesn't see red. It doesn't feel the redness.
This is the hard problem of consciousness.
Exactly. And digital physics frames the problem beautifully. It says, it's all information. But it doesn't fully explain how that dry, mathematical information ignites into the vivid internal experience of being alive, how syntax becomes semantics.
So we're back to the it from bit problem. We have a good theory for the bit, but the actual feeling of reality, is still a mystery.
It suggests that while digital physics might explain the structure of the universe, it might still be missing the inner life of the universe.
Let's talk about that structure again, because we've been very pro-digital physics so far, but there are some serious challenges to this view. We need to be balanced.
Absolutely. The biggest one is what's called the substrate problem. Or, more simply, what is the hardware?
Right. Information usually needs a medium, words need paper, software needs a hard drive, sound needs air.
Exactly. You can't just have information floating in a void. It has to be encoded on something.
So if the universe is information, what is it written on?
That is the million-dollar question. If you say it's written on quantum particles, then you're just back to saying matter is fundamental. You've lost the argument.
So what's the alternative? If it's not written on matter, what is it?
There are a few options, but they are all pretty abstract. One is mathematical realism. This is the idea that math itself is the fundamental reality. There is no physical stuff. There are just mathematical structures that exist independently.
So we are basically living inside a giant self-aware equation.
Yes. Another option is called self-instantiation. The pattern is the thing. It doesn't need a substrate. The organization itself is what makes it real.
That feels a little like a cop-out. It just is because it is.
It's a philosophical leap for sure, but think about it. If you demand a physical substrate for information, you end up with an infinite regress. What is the substrate made of? And what is that substrate made of?
Right. Eventually you have to stop and say, this is the bottom layer.
Exactly. Digital physics argues the bottom layer is the information itself. There's nothing underneath.
Okay, another challenge. Free will versus determinism. This is a classic.
It always comes up.
If the universe is code, and the laws of physics are algorithms, is the future already written? Is my choice to have a salad instead of a burger just the result of line 4000, subsection B in the cosmic code?
If the universe were a classical computer like Conrad Zuse thought, then yes, it would be strictly deterministic. Every effect would have a cause. But remember, the modern view is that it's a quantum computer.
And quantum means randomness, probabilities.
Correct. Quantum mechanics introduces true, fundamental indeterminacy into the universe. The future is not set in stone.
So I have free will. The universe is giving me a choice.
Well, hold on. Does randomness equal freedom?
Doesn't it tally?
Doesn't it? If it's not determined, then it's free.
Is it? If your actions are just the result of a cosmic dice roll, are you free or are you just chaotic? If a random number generator in the universe's code decides you get the salad, you didn't decide it. The randomness did.
Oof. Good point. Being random isn't the same as making a conscious choice.
Digital physics doesn't solve the free will problem, but it reframes it. It asks, can a computational process be an agent? Can a system of information reprogram itself based on new inputs? That's where the debate is now.
And finally, the biggest critique of all, is this even science?
The testability problem. This is a serious one. The philosopher of science, Karl Popper, said that for a theory to be scientific, it must be falsifiable. You have to be able to conceive of an experiment that could prove it wrong.
And if everything is information?
If any observation you make can just be interpreted as that's just how the information is being processed, then you can't disprove it. It explains everything, which means it might explain nothing.
It becomes metaphysics, a sort of religion for nerds. I wouldn't go that far. It does make some specific predictions, like the holographic principle predicting a finite information density, or the cellular automaton idea predicting a grid structure to space.
And we can test those.
We can try. We are building experiments, holometers right now at places like Fermilab to look for that pixelation of space-time. So it is on the edge of science, but it is trying to be empirical. It's not pure philosophy.
Okay, we've covered a huge amount of ground. We've gone from rocks to bits, from 3D space to 2D holograms. Let's try to summarize this entire exploration.
The core takeaway, I think, is the bottom-up perspective.
Right. We used to look top-down. We saw the complex world and try to break it down into smaller and smaller pieces.
Digital physics starts at the bottom. It says reality starts with incredibly simple rules. Binary choices, yes, no, on-off bits. And from those simple rules, applied over and over again billions of times per second, emerges the complex, beautiful, messy reality we live in.
Complexity from simplicity.
Exactly. And it suggests the universe is a self-simulating system. It's not necessarily some alien playing a video game. It's a system that computes itself. It generates its own reality, moment by moment, through the processing of information.
That is actually kind of beautiful. The universe isn't a static thing. It's a process. It's an active thought. It's happening right now.
It suggests we are not just things, but processes, part of a dynamic, evolving computation.
Which brings me to a final thought I want to leave the listener with. Something to chew on.
Go for it.
If the universe is a vast computation, and if we, as conscious beings, are part of that computation, then what are we doing right now? By studying physics, by asking these questions, by having this conversation and analyzing all this data.
We are the universe analyzing its own code.
Exactly. We are the subroutines that woke up and started looking at the source code.
That is a profound place to end. The system is becoming self-aware through us.
If you're listening to this, you aren't just an observer. You are the data understanding itself.
A fascinating loop.
Thank you for joining us on this analysis. It's been a mind bender.
Always a pleasure to unpack the universe with you.
See you in the next simulation. Or, next time.
Goodbye. Bye.